In this video, we're going to introduce what are called the product and quotient rules. Now, in order to apply the product and quotient rules, we actually have to remember our basic differentiation rules. So remember, you have a sheet that looks like this. It's actually a PDF version of this. You need to know all of these rules because we'll be applying them in the context of other problems. Derivative of a constant is 0. Derivative of a constant times x is a constant. You have a constant times a function. Just write down the constant and multiply by the derivative of the function. Derivative of x to some power is the power times x to the 1 less power. Derivative of a sum is a sum of derivatives. Derivative of a difference is the difference of derivatives. Derivative of an exponential, e to the x is e to the x. If you change the base, you just have to multiply by an extra natural log of a. The derivative of natural log of x is 1 over x. The derivative of log base a of x is 1 divided by the quantity natural log of a times x. Then these are the rules that we're going to learn today. We're going to do this in a different video. And then we've got the derivative of sine is cosine. Derivative of cosine is negative sine. Derivative of tangent is secant squared. Derivative of cotangent is negative cosecant squared. Derivative of secant is secant times tangent. Derivative of cosecant is negative cosecant cotangent. And then these six we will learn after we learn about implicit differentiation. Derivative of arc sine of x is 1 divided by the square root of 1 minus x squared. Derivative of arc cosine is very similar, just multiply by -1. Derivative of arc tangent is 1 over 1 plus x squared. Derivative of arc cotangent is very similar, you just multiply by -1. Derivative of arc secant is 1 over the absolute value of the square root of x squared minus 1. Arc cosecant is very similar, you just multiply by -1. Now it's a little bit difficult to see because of the way I've written this particular order, but the ones I want you to focus on are the derivative of arc sine, the derivative of arc tangent, and then the derivative of arc secant. If you know these three, and then the derivatives of the inverse cofunctions, will sort of come naturally because the derivative of arc cosine and arc sine are the same except for the sign difference. The derivative of arc secant and arc cosecant are the same except for the sign difference, and the derivative of arc tangent and the arc cotangent are the same except for the sign difference, at least in the formula. But we will apply all of these rules as we're practicing the quotient and product rules. It's actually really more of the rules in this column are more common than these. These are actually pretty common as well. But it's very good to have these committed to memory so that when we find the related antiderivatives in Calc 2, you'll actually know these things. I don't want you to just remember that you've forgotten them. I want you to actually know them when we need them. Okay, so let's talk about the product rule. If f and g are differentiable functions, the derivative of the product of f of x and g of x is the derivative of the first function times the second function undifferentiated plus the derivative of the second function times the first. And sometimes people list that in the opposite order. Rather than saying derivative of the first times the second, they might say first times derivative of the second. Either way, you're good to go. But let's write that out in words. This is the derivative of the first times the second function. And the second function, you don't do anything to it. You just write it down. And then we add the derivative of the second times the first. And remember what this is going to give you. This is a formula for the slope of the derivative of this or of this original function. So if we graph this function and we graph the slope and we graph the corresponding tangent lines, the slope of the tangent line should be given by the function on the right-hand side of this expression here. Now, typically, we write the derivative out like this when we're evaluating a derivative using the product rule. But we use this shorthand, we use prime notation. So we say derivative of the first times the second plus derivative of the second times the first. So this is what we have on our formula sheet, and this is the sort of version that we use whenever we're applying this. So let's look at a couple of examples, and then we'll look at the graphs on desmos.com to confirm. Let's say I want the derivative with respect to x of x to the fourth times sine of x. Whenever I see a function and I'm asked to compute a derivative, I ask myself, do I have a rule for that? If there's some rule in this sheet that allows me to take that derivative, well, I don't have a rule for that because these are all just derivatives of, or functions. This is the sum of functions. It's not a sum, it's a product. These are just trig functions with nothing multiplying them. These are inverse trig functions with nothing multiplying them. The only rule that we have for that is the product rule. So I look at this expression. The first thing I do is I identify the first function and the second function. This is my first function and that's my second function. And then I apply the rule. So according to the product rule, the derivative of this product is the derivative of the first function times the second undifferentiated. You just write it down. And then add the derivative of the second function times the first. You just write that down. And then we apply an appropriate rule. We say, do I have a rule for this? And we do. That's our power rule. The derivative of x to some power is that power times x to the one less power. So the derivative of x to the fourth is 4 times x to the one less power. 4 minus 1 is 3. And then we multiply by sine of x. And then we add the derivative of sine of x, which turns out to be cosine of x. And then we multiply by the x to the fourth. I don't want to write times x to the fourth here because then it might look like we're going to multiply the x and the x to the fourth and take the cosine of x to the fifth. That's not what we want. Since this is a polynomial and this is a trig function, we usually like to write the polynomial out front. So that's our result. And again, this is a formula for the slope of this function. So let's look at this function and then graph a tangent line and make sure that the slope of the tangent line agrees with the value of the function at the point of interest. All right, so here we are. This is the function that we were looking at. F of x equals x to the fourth times sine of x, and then we found the derivative using the product rule. It's the derivative of the first function, which is the 4x cubed, times the second, which is sine of x, plus the derivative of the second, which is cosine of x, times the first, x to the fourth. So those graphs are here. It's actually like kind of wild because this x to the fourth is a very large number most of the time, and sine of x just oscillates between -1 and 1. So in order to get a picture that looked like easy to analyze, I had to zoom in a lot. But we've zoomed in, and then I drew the tangent line. So that's y equals the original y value plus the derivative evaluated at our point of interest. So that's actually a number. It's just the slope times the change in x. You have change in y over change in x times change in x is change in y, and then you have change in y plus the original y value, which gives you the y value. So that's how you remember that formula for the tangent line. And I've graphed my tangent line here. So that's my original function, and then that's the point of interest, and that's our tangent line. So you might say to yourself, okay, well, what is the slope supposed to be of the tangent line of this function at this location? Well, you can just use rise over run. It looks like we go from about 0.2 to maybe a little bit less than 3.2. So maybe I'm going to say about 2.9 units is our increase in the y direction as our x values go from 0.5 to 1.5. So change in y is about 2.9. Oh, actually, it's not 2.9, sorry. It's 0.29 because these tick marks are about a 1/10 of a unit apart. So this is 1/10, 2/10, 3/10. So this is actually not, it's sort of 2.9 boxes, but each box is worth 0.1 unit. So 0.29 divided by 1 is our slope. And then we look at the value of the derivative there, and it turns out that the value of the derivative is 0.29. That's supposed to be a point on the derivative graph, which we can see if we actually graph the function itself. And so this formula for the product rule is actually giving us the formula for the slope of the tangent line of the original function at that particular location. And if we want, we can change the point of interest when x equals 1. The slope is the slope of this line, and I actually don't know what that is. I could calculate it using rise over run, or I could just go up to my graph. It looks like my slope is about 3.9. So if we go up 3.9 units, and that's going to be quite a few boxes from about 0.84 to 3.9 plus 0.84. And then 1 unit, increase 1 unit in the x direction, which is like from here to here because of the tick marks between the x values. Then we'll see that that's actually the slope of this tangent line. That's the idea. And of course, if you want, you can change that location. And it looks like the slope of the tangent and the function value are 0 at x equals 0, which is consistent with what we get when we substitute x equals 0 here. And of course, we could do that on paper as well. So let's actually use this to find the slope at x equals 0.5. So if I call this f of x, then f prime is equal to 4x cubed times sine of x plus x to the 4th times cosine of x. And we can evaluate that at 0.5. Now, I don't actually know any of these values. I mean, 0.5 cubed we could do by hand, but the sine of 1/2, I don't actually know. So I would use a calculator for this, probably a scientific calculator. Remember, this is the slope of the tangent line. So well, actually, I did it on my paper. We had 4 times 0.5 cubed times sine of 0.5 plus 0.5 raised to the 4th times cosine of 0.5. And we get that approximately 0.295 approximately as our slope, which again is the same as the function value at that x value. Alternatively, we could have just said f prime of 0.5, and we would get the same answer. Okay, so that's how we compute the slope of the tangent line just with pencil and paper. And if we wanted to find the tangent line by hand, we would just evaluate f at 0.5. So we'd have 0.5 raised to the 4th times sine of 0.5. We use a calculator to estimate that. And then remember that xy equals f at, or 0.5 and f evaluated at 0.5 is a point, or x naught, y naught is a point on our graph. So we're gonna have 0.5 and whatever that value is. And then if we want to find the equation of the tangent line, we just use point slope form. You have y minus y naught equals the slope times x minus x naught. And if you solve for y, you get that formula that I've been using on Desmos. So we're taking the original y value and we're adding the slope, which is change in y over change in x, and we're multiplying by change in x. So change in y over change in x times change in x is giving us a change in y. So we have change in y plus the original y value is the new y value. Our y value, y naught, is that value right here. We'll look at the calculator to figure out what that number is. And then we're going to add, this is all approximate, 0.295 times x minus 0.5 I just need to plug that in there and then distribute that 2.95 to the negative 0.5 and then collect like terms, and then that will give us the equation of the tangent line. So my function value at 0.5 is just f evaluated at 0.5, which is approximately 0.2996. Or I can use the calculator, that's 0.5 raised to the 4th times sine of 0.5. And see, we get the same number either way. So we can just use the function notation or this notation and it's going to give you the same answer. So that is our y value. I'm just going to substitute that in here. I'm going to write approximately 0.2996 0.02996. And then later when I distribute that x minus or that f prime at x naught to x naught, I'm gonna have 0.295 approximately times that negative 0.5. And I'm just using this desmos.com as a calculator now. And then I've got two like terms, that negative 0.4175, and then the function value, that f evaluated at x naught. And that's approximately negative 0.11754 plus 0.295. I want to show you my piece of paper now. I'm just using the calculator here. So these are just the answers that I got from the calculator. This was equal to this. So that means our x naught, y naught is this point. Then I solve for y with my point slope formula. And then I substitute in my y naught. I substitute in my x naught and my slope, which we calculated earlier using the calculator. Then I distribute. And then those two terms are just constants, so they're like terms. So that is an approximation of the tangent line. Let's graph it on Desmos and make sure that we've got the right answer. Okay, so we stated the formula right here. That's taking our point slope form and then adding that y naught, which is f of x naught, to both sides. I claim that this line, this purple line, is the same as the line I'm about to type. So my y was approximately 0.295 times x minus 0.11754. And I think we can see that those are basically the same line. We lose a little bit of accuracy because this is using the exact value of that function and the exact value of that. And we used estimates for f of x naught and f prime of x naught when we did our calculations by hand. But you can see using pencil and paper, you get the same answer. All right. So that's just to emphasize that this equation that we came up with using the product rule is a formula for the slope. Got our formula for the slope, and then here we're finding the equation of the tangent line. At a particular x value, in our case, it was x equals 0.5. And we see that the calculator and our handwritten calculations give you the same answer. Okay, so back to the product rule. We're not going to do this anymore, but remember what this is. It's a formula for the slope of the tangent line at a particular point. In order to find that formula, if we have a product, we take the derivative of the first, multiply with the second undifferentiated, and then we add the derivative of the second times the first. So let's do another example. We have the derivative with respect to x of let's use e to the x times tangent of x this time. This is our first function, and this is our second function. So according to the product rule, we have the derivative of the first. times the second undifferentiated plus the derivative of the second times the first. I like to write it this way because it reminds me which derivatives I need to compute before I finish the problem. This derivative is just an e to the x. And the derivative of tangent of x was one that we explored graphically. That turns out to be secant squared of x. I'm going to put some parentheses around that. So what we end up with is e to the x times tangent of x plus this e to the x times secant squared x. Whenever I have an exponential times a trig function, I like to write my exponential out front so that it's clear that this function multiplies this function and we're not taking that e to the x and multiplying it by the x inside the trig function. So again, this is the formula for the slope of that function. We can graph this function and graph a tangent line at a particular location and see that this is actually giving us the right slope for that function. Okay, so this is our function. And if we zoom out a little bit, we can see more features of it. We've got e to the x times tangent of x. Now remember, tangent had all of those different branches. So it has tendency to go from negative infinity to infinity over the interval from negative pi over 2 to pi over 2, and then it repeats. So it always has those asymptotes, and then we're taking it and multiplying it by an exponential function, which is very, very large as x gets large, and then it's very, very small as x goes to negative infinity on the other side. So you end up with this kind of weird thing where you're taking very large numbers and multiplying them by those branches of the tangent function, and then very small numbers and multiplying them by the branches of the tangent function. It looks kind of like this. But if we zoom in and we say, okay, well, what's the derivative look like? The derivative of this is this orange function that we found using the product rule. I'm interested in x not equals 0. So I'm looking at this point and I want to find the slope of the tangent line there. It looks like the slope of the tangent line is supposedly 1. And the tangent line is like this. And look at that perfect line. Now, rise over run is we just go up 1 and over 1, up 1 and over 1 to get to another point on the line. So yes, the line has a slope of 1, which is the same, undo. This is the same value that we get when we substitute in a 0 to this function here. You get 1. It's e to the 0, which is 1, times tangent of 0. Tangent of 0 is 0. So this part is 0, plus e to the 0, which is 1 times secant squared of 0. Secant squared is actually 1 over cosine squared. So 1 over cosine of 0 squared is cosine of 0 is 1. So we have 1 over 1 squared, which is 1, times e to the 0, which is 1. So you end up with 1 times 1, which is 1. So you get 1 there. Now you can also move this little guy around and see that at different locations, this slope is different. At x equals approximately negative 0.8, the value of our derivative is approximately 0.463. So we can see that, and we can also estimate that graphically if we want to at various points on the curve. Okay, now let's do one last example of the tangent rule, or excuse me, tangent rule, product rule. So I've got the derivative of x squared minus 2x plus 5 times natural log of x. Actually, maybe we'll just do the product rule in this video. I've got a polynomial times a logarithmic function. So this is my first function and this is my second function. Whenever I apply that product rule, I say to myself, the derivative of the product is the derivative of the first times the second undifferentiated. So you just write down that logarithmic function, you leave it alone, you're not going to do anything to it. And then you add the derivative of the second times the first. Make sure you have parentheses around that first function because it's got multiple terms. And then we evaluate this derivative and we evaluate this and we actually multiply them. So for this function, I've got a sum of terms. So we're going to use that derivative of a sum rule. So we say, do I have a rule for x squared? We do. We bring the power down, multiply by x to the 1 less power. So the derivative of x squared is 2 times x to the 2 minus 1, which is 2x to the first. And then we subtract the derivative of that constant times x. The derivative of a constant times x is just the constant. And then we add the derivative of the constant. Well, the constant function is just a horizontal line, so the derivative is 0. Or we can just memorize that the derivative of a constant is 0. So I've got this times log of x plus and the derivative of natural log of x, which is 1 over x, times the original function. Or not the original function, the original first function. And then you can simplify wherever you can. Of course, this can be simplified as just 2x minus 2. The natural log of x is still there. And then you can leave this like this if you want to, or you can write it as a quotient. I think I'd rather write it as a quotient. You also have the option of, rather than writing it as a quotient, of simplifying. You could do the x squared divided by x equals x, and then the 2x divided by x is negative 2 and the 5. So you've got this version is one possibility, and then you have this other version, which is another possibility. So you've got 2x minus 2 times natural log of x plus x squared over x, which is x, negative 2x over x, which is negative 2, plus 5 over x. So either one of those is fine. And again, remember, this is the formula for the slope of this function. We can graph both of the functions and look at the slopes, and hopefully the value of this function at a particular location is actually the slope of this function. Okay, and for this last example, we've already done our calculations, but I just wanted to show you at x equals 1, the graph looks like this. So this is the graph of our function. You might be interested in the tangent line at that location. So I draw a tangent line and I plot the point on the line. We can label it if we want to. You might say, okay, well, what is the slope of the tangent line there? Now we have to be careful because the subdivisions in the y direction represent 2 units and they're a certain distance apart. And the subdivisions in the x direction are actually longer, but they're a certain distance apart. Like one of these tick marks represents 1 unit and one of these tick marks represents 2 units. So when you read the graph using the grid, you just have to be careful about how you interpret those values. So we're going from this location to, let's say, this tick mark. So we're going from x equals 1 to x equals 4. So the change in x is 3. And then the change in y is the distance from the x-axis up to this location, which is about 12. So I've got 12 is change in y divided by 3. So I would expect a value of 4. Here's f prime. And it turns out that at x equals 1, the value of the derivative is 4. So we know that when we're doing this correctly, the slope of the tangent line is given by the values of the function on the derivative graph. And this is just the version of the derivative that was simplified the second time. And of course, if you want to, you can change the x values and see the different slopes on the derivative graph. Or if you wanted to do these calculations by hand, you can always actually plug in, 2 times 1 minus 2 times natural log of 1, which is 0, plus x equals 1 minus 2 plus 5 divided by 1, and you get 4. So you can do that by hand on paper if you want to. You can use the calculator to do it. Or you can just say f prime of 1 and see what the value is. And if you want, you can move this around and look at the graph and read the graph to find the function values, or you can just switch this notation here to f prime of x naught and then see how that slope changes as we substitute in different values of x, and how that is consistent with both the slope of the tangent line and the function value for the derivative graph. And again, the derivative is the orange graph, And the teal graph is our original function, and we've got our dotted line as our tangent line. So I think we're gonna stop there. We'll do the quotient video or quotient rule in another video. But just remember, whenever you're applying these rules, derivative of the first times the second plus the derivative of the second times the first for the product rule, the whole point is to find another function that gives you the slope of the original function. And we're just emphasizing that by looking at these graphs.